My pleasure to introduce our seminar speaker today, Ed Olson. Ed did his PhD at MIT and has been a faculty member at the University of Michigan for the last 3 years. Some of you know him because of his work on April tags, which are these wonderful fiducial markers, which are revolutionizing navigation in my technical system. And I know several other labs at CMU have also adopted them, and I think they're going to have a big impact. And it's open source, so that means Ed and I go to the same church. But today he's going to talk about the magic competition and how he won more than $750,000 by winning the magic competition. So, Ed Olson.
Hey everybody. It's fun to be here. I've never actually been to CMU before. Just ran into you guys at DARPA Grand Challenges and things and shake my fist in quiet fury. All right, that's an ominous beginning. So I'm going to talk about Team Michigan and the Magic 2010 robotics competition. You guys probably already know the backdrop for this. There was a congressional mandate in 2001 that a third of all ground combat vehicles need to be unmanned by 2015. And yes, laughter begins. So DARPA realized that this was a bit of a joke, and they started with these desert races. I won't tell you how the 2004 race turned out. I think many of you already know. But 2005 was pretty remarkable. 5 teams finished a 132-kilometer course. Very exciting. And then Urban Challenge, which you might have also heard of. That was fantastic. So in my mind, we moved from sort of GPS breadcrumb tracking to operating in an urban environment, finding paths, dealing with moving obstacles for the first time. Really an incredible leap in the sophistication of the autonomy that we saw in the robots at that time. And I think this is my favorite picture from there. It doesn't happen to correspond to the finishing order, but that's our vehicle there. All right, so fantastic, right? Well, it's 3 years later. It's 2011. 2015 is right around the corner. So you might say, how are we doing with regard to this original congressional mandate? So you go out and you look at the robots being fielded by the military, and what you see are GIs with their hands and faces buried in these operator control units, teleoperating joysticks, teleoperating robots with joysticks. And this is a problem, right? So we can technically satisfy the congressional mandate by teleoperating. It only says unmanned. But I'm going to assert that we really need autonomy anyway. A couple reasons. It's really hard to teleoperate a robot. When you're looking at a tiny little video screen, you become disoriented. You don't really know what's going on. This little photo over here, this happens to be one of the magic competitors from Turkey. At one point during the middle of the competition, the robot just jerked forward and drove straight up onto an obstacle. Now, it turns out this happened because the operators had just put the robot in teleop mode and driven it, right? And the humans did worse than their autonomous system. So it's really hard. Another problem is that personnel requirements are really expensive. You typically have 2 or 3 operators per packbot in theater right now. And take those two things together, you've got slow operation, large manpower requirements, and you find out that it's just too slow, too expensive, that when it matters most, whether we're talking search or rescue or whether we're talking clearing a village of IEDs, robots are just too slow. So that's a problem. And that brings us to ask a few questions. What went wrong? Why was it that the technologies in the DARPA Grand Challenge didn't transfer better to the robots that we actually see in theater? So there are a couple of reasons. I think, first of all, we relied too much on GPS and prior information in the DARPA Grand Challenges. If you're in an Afghanistan village, you can't ask Google where the directions are to the IEDs. It doesn't work. And we also want to be able to operate indoors in places where GPS might be denied. It's very, very easy for the bad guys to jam GPS. Another problem is that the DARPA Grand Challenge and DARPA Urban Challenge, these were 100% autonomous systems, which turns out not to match what the military wants. Right? In every case where we deploy robots, there's actually a human somewhere who wants to be in control of those robots. So this notion of sticking the USB key and the robot goes and does something, comes back, it's actually a mismatch. We want the human commanders to be in control, and not to, but to use autonomy to reduce their workload, not to take them out of the loop entirely. And the other aspect that was overlooked was the multi-agent side. So how do we deal with planning and coordination amongst multiple robots? And how do we deal with communications, which now emerges as a major technical challenge? All right, so to address these problems, we have a new grand challenge in robots. It's the Magic 2010 Robotics Competition. It was sponsored by RDECOM, which is sort of the Army's DARPA, if that makes sense, as well as DSTO, which is the Australians' DARPA. It was open to teams around the world, and the basic idea was to explore and map a 500 by 500 meter area. That's this, right? It's a pretty large area. This is a horse track, a horse racing track. And as you go through, build a map. We're looking for objects that are interesting, where some of those are hazardous, some of them aren't. We're cataloging them. If we find an IED, we're going to neutralize it. And a big difference between this and the previous competitions is that human operators can help. You're allowed 2 human operators, and they can intervene when the robots do something wrong. They can provide additional information, revise the, tweak the autonomous planners. But you pay a huge price for that. Every second that you interact with the system, you're hemorrhaging points. And then why would we do it? Because it's a great problem, and there was a lot of prize money. So off we go. The objects of interest that we're looking for in this competition are not real-world IEDs. It's going to be a long time before a robot can look at a backpack crumpled against the wall and decide that that's a dangerous-looking crumpled backpack. So for the purposes of this competition, IEDs were these little red trash cans. And there were rings painted around them. The robots couldn't see the rings or weren't intended to. But the innermost ring represents a detonation range. So if your robot were to go within that nearest ring, the IED blows up, and you lose all of your robots within like a 30-meter radius. If you get between the second ring and the first ring, you can bring a special robot there, one with a laser pointer, point it at the target, and neutralize the target. So we're interested in finding and neutralizing as many of these guys as we can, finding and neutralizing mobile bad guys. Here's a mobile bad guy blowing up a robot. And cataloging as many other objects of interest that we can. So a toxic vat, a gas can, a barrel, and parked cars. So no moving cars. The only moving things were the people. OK, so that's the overview of the competition. The timeline, this was a very short clock. I'm standing in half of your guys' way. Maybe I'll do this. Can you see better? All right. So Magic was announced in July of 2009. It attracted 23 teams from 5 different countries. There were 3 phases of competition. The first one was a written technical proposal, which thinned the team down to 12 teams, and then 10 of those actually got a little bit of money to begin development of their systems. That brought us to June, so a pretty good chunk of time between the technical evaluation and the site visits, where the judges came out and they evaluated your system. And they reduced from the 12 teams down to 6 teams. Then we have from June to November to finish everything else, get our robot system from the US to Australia, which is no mean feat. And then there was the final competition in November, which I'm happy to say resulted in just 1 team left. So that was very exciting. Yay. OK, so I want to introduce you to some of the teams that were finalists. Most of you probably know Dan Lee, UPenn. He does great work. This was his team's here. Kind of an interesting thing about his team was that they made the video part of their original proposal available online. And he's done a lot of this sort of stuff before, so we were terribly intimidated because he has video where the robots are doing this sort of stuff. Cappadocia, this is a Turkish military contractor. They were really interesting. They had beautifully engineered systems, and they were the only team to use RTK GPS. And they had an interesting solution to the communication problem. We had joked on our team that, why don't we just get a bunch of cell phones, and use the cellular network as our messaging system. And we decided in the end that wasn't a good idea, because who wants AT&T between you and your robot? Or Verizon. So they had an interesting solution. They brought their own cellular network. So the first day they showed up, they erected this base station. They had their own 4G WiMAX thing. So they had 40 megabits per second of bandwidth to their robots. Which didn't occur to us. Razor, this was a team principally run by Robotics Research. They were the only people to actually have a combat-relevant platform. This is Kinetic Talon. And I believe some people at CMU were at least loosely involved in that team. Beautifully engineered machines. Magician was a consortium of Australian universities. In the end, they didn't do that well, but one of the interesting things about their team was that from an underlying technology perspective, like the way that they built maps and the way that they distributed tasks, they had a lot in common with our system. So I was actually pretty impressed. And then Team Michigan, which is going to be the focus of this talk. So Team Michigan was principally run out of the University of Michigan. We had an army of undergrads, a fraction of which are here. We actually had about 30 undergrads, which are great, not because they're individually super productive, but because they're free. So we made up for quality with quantity. That's an exaggeration. They actually did a lot of great work. And we were very glad to have them. We had 30 undergrads divided up into teams around 4 or 5. They did initial versions of our navigation system, initial versions of our vision system, basically roughed out prototypes of everything. And then around June, we trimmed down to fighting form, and this is the group that actually went to Australia. We had one non-university partner, which was SOAR Technologies. This is a spin-off of Professor John Laird's research. It uses SOAR, the cognitive architecture. OK, so you've just entered Magic, and you want to ask yourself, how hard is this problem? Right, so we had some experience with Teleop, and we had some experience with DARPA Urban Challenge, and we kind of figured, well, Magic's got to be somewhere in the middle, right? We want to do full autonomy, but if we get stuck, we can ask the humans for help and just pay the penalty. Well, that's what we thought. It doesn't really work out that way. As you start building the system, you really realize it's harder than that. If you need the system to be able to be autonomous anyway, right? And then you want the human to be able to interact as necessary, as they choose to, right? You don't want to force the human to get involved. So in addition to building a system that is fully autonomous, now you have to build extra stuff to keep the humans involved in the loop, be able to query them for information, get that information encoded back into the system, and integrated with the planning system. So this was kind of a surprise for us as we thought about it. It's a harder problem. All right, so let's start with a very quick overview of how our system works. It's a centralized planning system that's actually more or less mandated by the design of the competition. We have a base station with a big pile of laptops, five of them or so. And we collect all of the data from all the robots at this place. We take all of the little map tiles, we composite them together into a big mosaic. We try to maintain a coherent coordinate system for all 14 robots. And then most of the time, what we're doing is autonomous exploration. So we're figuring out where we haven't been. We're assigning robots to the frontier in an attempt to jointly maximize the amount of frontier that we're going to explore. Now, the commands are sent to the robots at a very high level. So the robots will get over the radio a command like, go to lat long XY. And the robots are individually responsible for carrying out that mission. So the robots have a sensor system. They build up a 3D model of the world around them. They figure out where it's safe to drive and where it's not safe to drive. They are on the constant lookout for these objects of interest, including, in particular, the hazardous ones. With 14 robots, you can't rely on a human looking at 14 video streams to find these things. It doesn't work. And then the robots are carrying out these commands. Then they broadcast all this telemetry back to the ground control station, which composites an even bigger map of the world, generates new plans, and the process repeats over and over and over. By the way, if you guys have questions as we go, I'm happy to keep this informal. Anything so far?
Why 14 robots?
Why 14? Well, so we wanted to make sure that we would stand out. So one of the things we figured we wanted to stand out, and the way we figured we could stand out would be to show off our autonomy at a scale bigger than what we thought the other teams were going to do. So somewhere the number 15 came about, and then that turned into 16 because it's a power of 2. Nice round number. And then we got to Australia, and 2 of those robots migrated into spares, hot spares. So we ended up with 14. And the gamble worked out. We had 14 robots. Penn, which had the second most, had 9. So right off the bat, if you kind of look at a pile of robots, one of our litmus tests is when you looked at the robots, we wanted you to not be able to instantly tell us how many robots there are. Right? When you look at a pile of robots, if there's 5, you're like, that's 5 robots. 7, you're probably like, well, that's 4 plus 3, it's 7 robots. At 14 robots, you look at it and it's like, that's a lot of robots. Very scientific methodology there. All right, here's a trailer of our system. This is about 98% autonomous. We've got the robots started down here. And they're basically just constantly spreading out towards the frontier, exploring as we go. As we go, you'll see that the map is sort of adjusting and jiggling itself into alignment. That's our SLAM system working. It's fixing most of our misalignments. That little 1,000 that pointed there, that's an object of interest that we detected that was assigned ID 1,000 for no good reason. They continue to explore along. Just for scale, this little rectangle here, this rectangle too, that's a car. So this is probably about 100 meters, and this is maybe 30 meters. And this mission took about 20 minutes of real time. So this was one of our early runs, and we were pretty excited about it. This actually shows the graph structure for those of you who are SLAM junkies in terms of the graph that we were optimizing. I'll talk a little bit more about that later. But that's the behavior that we want. One of the keys to our success was to be able to really be able to iterate our robot platform a lot. We wanted to build a large number of robots, and so going out and buying Talons or Packbots was just out of the question. We quickly realized that our only option was to build our own robots, especially given the small amount of money that we had. We started off with some really lousy differentially steered robots. These are great indoors but terrible outdoors. So we pretty rapidly migrated to a 4-wheel platform. This one, which you can't really tell from the photo, is it's really held together with more duct tape and zip ties than anything else. So that took us to February, and by April, we had our first rapidly manufacturable version of this chassis. So our entire chassis can be printed out on a laser cutter in a couple hours. You just load up the wood, hit print, which is great for computer scientists, and glue it together, slap in the motors, and off you go. And it was a good investment because we were able to take this design and keep tweaking and fixing bugs. So we ended up with a platform that looked like that, and then our site visit robots looked like that. And finally, we built our final fleet of 24 robots, which was the 16 we intended to ship to Australia, plus 8 more for us to continue doing testing on while the 16 robots were on the way to Australia, which takes weeks. So it's a lot of robots. All right, so first little quiz. What do these two platforms have in common? Wheels, yeah. Literally, they are the exact same wheels, right? So we were trying to figure out how to make a reliable drivetrain, and we figured, well, who wants to make a reliable drivetrain? Well, any company that sells a product under warranty. So our lab took a field trip to Sears, and we're crawling around on the floor looking at the drivetrains for the lawnmowers, and we liked what we saw. So this drivetrain is lifted directly from this lawnmower. It did lead to kind of a funny moment when we called the Sears home repair hotline, and we said we need to order a replacement wheel. They said, how many? And we said 80. That was kind of fun. So the ability to rapidly iterate was a really good thing for us. We had some interesting failures early on. This was our February robot. It was doing an autonomous mission, and one of the wheels just came loose and rolled down the sidewalk. The robot at the time had no idea that had happened and just kind of kept dragging itself like it wasn't very good. And this is kind of key, right? With 14 robots, mean time between failure is a big deal, right? If you have a mean time between failure in your lab of maybe 40 hours, that might be okay. Every week you have to go and twiddle and tighten a screw. But with 14 robots, that means you're fixing something every 3 hours. So we took that pretty seriously. The problem here for you hardware junkies, set screws suck, right? So this was another failure. This is the robot's view. During the site visit, the judges had this obsession with ramps, like from the NIST, the NIST urban rescue thing, and newspapers too. We couldn't figure it out. But our robot's slowly going up and over, and then it gets to the top, and it kind of guns it with an unfortunate consequence that it actually does a front flip. So this was a failure mode that we discovered fairly late on. This is June, with only a couple months to go. Turned out that we just had too short a baseline distance. So we had a rapidly manufacturable system. We could just stretch out the chassis, and a couple weeks later, we had a new batch of robots. So that was very cool. Inside the robots, we had what we like to joke is an undergrad-proof battery. This is an important thing. It's a 720 watt-hour lithium iron phosphate battery. It's good for about 4 or 5 hours of the robot actually chugging around, which in reality is more like a whole day's worth of development. Our hard real-time stuff was done on 2 little ARM microcontrollers, one here and one here. Everything else was basically plumbed together with Ethernet and USB, and then we just threw down an off-the-shelf laptop on top. Right? You can't beat a laptop for cost-effective compute. The whole design is actually open source. We're publishing documents for this. The chassis itself, the actual mechanics, cost you about $500 to build one of these robots. It's not going to compete with an ATRV or an RMP 400, but for $500, you can do quite a lot with it. All right, so a little more about how the system works. So we did one thing that was fundamentally different than all the other teams. Most of the teams, all the teams are allowed 2 operators. And so what most people did is they built 2 operator controls units. And then they sort of divided up the robots amongst the operators. One operator would handle robots 1 through 5, and the other ones would handle 6 through 9. We did something a little bit different. It started off with the realization from playing StarCraft. You guys play StarCraft? Yeah, yeah. So think about you're playing StarCraft. In StarCraft, you have good situational awareness of what's going on. It's actually not hard to keep track of 200 units. Right? You can do that. If you can maintain a consistent coordinate frame where everything's lined up, 200 units is not a bad thing. And actually, StarCraft's a good analogy for this. Right? The human can inject information. I want these guys to go over in this direction. But most of the time, you can just leave them to what they want to do. The SCVs do their thing. They do path obstacle avoidance and that sort of thing. So that was our model. We realized right away that one person was going to be completely sufficient for doing the task allocation and being the man in charge, as long as we could maintain a coherent coordinate frame between all the robots. So that's where our second operator came into play. He was basically a slave to the system. His job was to make sure that the SLAM system didn't go wrong. Right? If the SLAM system missed an edge where it needed it, he could go through and suggest loop closures. If the system saw an object of interest and it wasn't quite sure about the classification, it could pop up a picture, and the sensor operator could help classify it. So this guy's job was basically to make sure that the task operator had this StarCraft-like interface where everything just was working. Now, our long-term vision here is that this guy is going to have less and less to do, but we've got some time to do that. I think this is a good way to do it. As I mentioned before, human interaction is really penalized in the system. There was literally a line painted on the ground that was a meter away from the keyboard. And there's a guy with a chess clock, and when you step across the line and to interact with the computer, he's timing you. And they take the number of seconds, they multiply it by a constant, and they subtract that from your score. So there's a real incentive to stay behind that line. You can notice here that everybody had big monitors, right? And so you could actually see what was going on from a meter away. The exploration planner was basically our main autonomous planner. There's really not a whole lot fancy to this. Those of you who've implemented a frontier-based exploration system have implemented this system. You just keep sending robots to the closest point that you haven't yet been. Wash, rinse, repeat. And it turns out to work pretty darn well. All right. Now I'm going to switch to talking about what was going on the robots. So what we've seen so far is that we've got the ground control people. They're working with the autonomous planner to figure out what commands to send to the robots individually. So the robot receives a command of the form, go to lat long XY. And so the robot needs to figure out where it's safe to drive. And we built this sensor head here, which combines a 30-meter Hakuyo. I'm assuming everybody's familiar with these sorts of things. It's on a servo, so we can build up a 3D point cloud. We were building point clouds at about 0.7 hertz. So these are about 40,000 point clouds. And it was co-calibrated with this camera, so we could do RGB color for every LiDAR point. What that allowed us to do was to do object segmentation of what we were seeing in the world, breaking up objects based on their geometry, how smooth they are, what their surface normals are, what their color and texture are. And that would be the beginning of our object recognition. We'd segment the world into these little pieces. We could compute a bunch of features corresponding to each of the separate objects. Here, so what you're seeing, every object that's colored uniformly, this is one extracted cluster. This is an extracted cluster. And the nice thing here is that it really corresponds to sort of the natural segmentation. By combining both the LiDAR and camera, the segmentation becomes much easier than with either LiDAR or camera alone. So how did we actually do the object classification? Well, we would take those extracted clusters, those extracted objects. We'd compute a bunch of features, classic sort of a machine learning approach. Our features were things like, what's the average color? What are its physical dimensions? How pointy is it? Does it have lots of corners? And how well does a circle approximate it? That was a good one because we knew that a lot of our targets were bins. That fed into a classifier, and out came our classifications. So here what we see is the robot tootling along. It identifies a couple people over here, which I think is actually pretty cool because you can hardly even make them out as a human from the point cloud. And then we detect one of those hazardous bins over here. So a pretty straightforward system. The nice thing was, the key idea here was that by combining the LiDAR and the camera image at a very low signal level, we made the classification problem much easier than it would have been otherwise.
As you can see on our task GUI, Sensor Robot 6 has detected an OI here as marked by the concentric circles. Disruptor Robot 15 is waiting nearby to begin the neutralization process. We will task it inside of the neutralization range so that it may begin the neutralization process once we give it the final OK. Disruptor 15 is now getting in position. It is in position. We will now allow it to begin the neutralization process. You can now see that the laser is enabled as marked by the bright red line. The wide red line indicates the target has been acquired.
All right, so that's an example of a live target neutralization. The main thing I want to point out here is that this whole process was about 2 mouse clicks. Right, so hopefully for the foreseeable future, we'll have humans involved in the loop before we actually start shooting things. So one of those mouse clicks I consider free and good. Basically, what happens is the system, you say go. You assign the frontier-based exploration planner to all the robots. One of those robots found the bad object, automatically dispatched a neutralization robot to come close by, and then a human actually gave it the authority to neutralize it by moving within range and turning on its laser. So this is what that scene actually looked like. I've got our robot here, and you can see there's a little laser pointer. On our laser mount, there's just a standard eye-safe laser mounted cofocal with the camera. All right. So that's kind of a quick overview. I think really the main challenge of the whole contest was maintaining this consistent coordinate frame. I've mentioned that a couple times. And to me, as a person who comes from a SLAM background, this is one big SLAM problem. Now, it's really hard to maintain a consistent coordinate frame with 14 robots under autonomous control doing silly things for 3.5 hours. Right? So this was the real challenge that we had to solve in order to make the whole rest of the system work. Right? If you know where everything is, planning's not that hard. Right? So how did we do that? The other thing I wanted to mention is that in terms of human interfaces, if you want to keep the human commander aware of what's going on, there's no better way to do that than with a metrically accurate map. Right? So topological mapping methods weren't really viable in this application. So how many of you have done SLAM or are pretty familiar with it's probably half. I'm going to give you a 30-second SLAM review. All right, so we've got a robot. It's driving around this trajectory. It's got some positional uncertainty, which starts off kind of small and grows over time. All right, so as the robot's driving around, we might recognize some landmark in the environment, in this case, the Eiffel Tower. And that's useful because later on, we might observe another object, which we might recognize as also the Eiffel Tower. Now, if I've seen the Eiffel Tower from 2 different places and there's only one Eiffel Tower, then that's actually a useful piece of information because I can constrain these 2 observations of the Eiffel Tower to be at the same physical location in space. Now, what that means is that if you consider this as sort of a graph, I now have 2 ways of computing the position of this node. I can integrate the motion around the loop, and I can integrate the motion taking this shortcut. So if you think of this as sort of a least squares optimization, I've got an over-constrained system. Right? I've got two ways of measuring the same quantity, and the more ways I can get to compute the same quantity, the more I can average out the error. So the short version of the SLAM problem is that I want to go around, I want to recognize places, match them together, and over-constrain the trajectory of the robot as much as I possibly can, because that's going to lead to a better map. All right, so the key questions are, where do we get these edges? Where do these edges come from? And there are three basic ways that we did it. We did inertially aided dead reckoning. We used camera-based fiducials and map matching. So I'm going to talk about this very quickly. The dead reckoning was pretty straightforward. We had a skid-steered vehicle, four-wheel skid-steered vehicle, which means that its odometry was terrible when we were turning. So we used an IMU to estimate our yaw. This is a little open-source IMU that you can download the Gerbers for in the firmware. It's about a $250 board with performance comparable to an Xsense, if you've used one of those. So we used the IMU and we used the wheel encoders to give us a chain. Right? This is how our graph begins. There are no loops, nothing's over-constrained, and so our uncertainty grows quite rapidly. So we still need some way to add additional edges to this graph. So the first thing we did, we had this April tag thing floating around that we'd been playing with for a while. So one of my students suggested, well, why don't we put some April tags on the robots? And you guys probably noticed by now that all of our robots have these little goofy 2D barcodes. These are similar qualitatively to QR tags and things like that. Or if those of you have used AR Toolkit or AR tags, it's a similar system. But since you guys are roboticists, you'll appreciate how much harder the problem is in uncontrolled environments, where your lighting is crazier. You might be viewing it at worse angles. April tags basically brings a much more robust detector and also a much stronger coding scheme into that barcode. It can handle more errors in it. So we use that, and so when one robot sees another robot physically, we see the April tags, and we get the 6 DOF position of the other robot by observing the April tags. It's pretty cool. Had an effective range of about 4 meters. But of course, the real money way of constraining these things is to match the maps that are being produced by the robots individually. Right? So the problem with April tags is 2 robots have to be in the same place at the same time. That's quite a constraint. So what we wanted to do was to be able to take the little map units that are being generated by each robot and be able to compare them over time. This is basically a scan matching method. Just to motivate it, imagine that we had a robot. It kind of drives up here, gets way up off screen, and comes back down, and it's accumulated some positional error as we go. So we've got sort of a ghost image of the same hallway in 2 different places. That's not what we want. What we want to be able to do is take those maps, pull them together, and get a consistent map that looks like that. This is our goal. Now, here's the challenge. People have done scan matching for years. We have a slightly different situation going on here in that the rate at which we need to do the scan matching is orders of magnitude higher than on a single robot. Right? First of all, we have 14 robots going along. They're accumulating dead reckoning error at a really horrendous pace because they're under autonomous control. They tend to do silly things like slip in place on leaves and things like that. So their dead reckoning information is terrible. They're accumulating uncertainty really, really rapidly. And every time a robot sends you a little tile of map, you need to attempt a match between that tile and every other tile that might overlap with it. Right? So this really rapidly becomes a large number of comparisons. Our previous best scan matcher, which I think is probably one of the fastest scan matchers available, based on multi-resolution scan matching, correlative matching, could handle about 50 hertz. That's just not fast enough for this application. So we had to do something about that. Those of you who have seen iterative closest point, this is kind of the classic way of doing it. The basic algorithm is you take a point, you look for the nearest blue point, and then there's a nice little math trick that if you have known correspondences between 2 sets of points, you can in closed form compute the rigid body transformation that aligns them best. Now, your data associations may not have been quite right, so you repeat the process, hopefully drifting into the global minimum. The problem is, this doesn't really work. First of all, it's not probabilistically grounded. It's doing this sort of goofy spatial search, and you don't really know what you get at the end. You can also get stuck in these sorts of local minima it doesn't matter how long you let this run, these red points are never going to get pulled over to these blue points. Right? You've gotten a local minimum. So you can actually visualize the error of an iterative closest point scheme with a graph like this. What this is showing you is the average error in Z as a function of the rotational misalignment and the translational misalignment. So we see if for small misalignments, we have low error. ICP works well if you're not far off to begin with. But as you increase the rotational error or the translational error, you end up with more and more error. Right? Your scan matcher is more likely to get caught in a local minimum. All right. So we wanted to do this in a more probabilistic way. Some of you have probably seen this particular Bayes net before. What we're really looking for is the probability distribution for where we are now as a function of where we were before, our control inputs, our laser scan observation, and some model of the environment. So we can look at that this way. Where we are now is a function of where we were before and our control inputs. This is the model of the world. So what we see is a function of where we are and what the world looks like. So we can apply Bayes' law and manipulate this thing around as the product of two things. This term here is kind of handy. It's the observation model. Right? It's what's the probability that I see what I saw if I assume I knew where I was and I assume I knew what the world looked like. Right? We can compute that. We know what the noise model is for a SIC or a Hokuyo. We can also compute this term. This is the motion model, which is the probability of where I am now, given where I was, and how I told the robot to move. Right? We have a noise model for that as well. So the game here is that we can formulate scan matching as a search for the x sub I that's going to maximize this probability. All right, so this is what that looks like. X of I has 3 degrees of freedom, right? We've got translation in X, a translation in Y, and a rotation to deal with, which gives us a 3D search space to work in. This is that 3D search space for this particular scan matching problem. Each individual tile corresponds to a fixed rotation, and then looking at all the translations in that rotation. And you can see that the maximum likelihood solution is right over here. So this is what we'd like to do, but it's completely impractical because of the ridiculous number of alignments that we have to compute and the number of terms that we have to evaluate for this probability distribution. And of course, the larger the volume is that we need to search over, it's going to just get worse and worse. So the new work that really enabled us to match maps even faster than before was a multi-resolution matching where we've extended this to be a whole image pyramid of map slices. I'm losing my perspicacity. All right, so we might start off with the finest resolution. We can decimate that using a max operator. You know that you wouldn't want to use the ordinary image processing decimate operator because by the time you get to this level of resolution, you're just going to have black. Right? You would filter out all of this stuff. So by using the decimate with a max operator, what you guarantee is that when you do an alignment with a coarser level of resolution, you're going to strictly overestimate the quality of an alignment at a finer resolution. So now you can organize a really simple little search based on a heap and just keep pulling out the most promising candidate, which looks a little bit something like this. Now this is a gratuitously slowed down version. What you're seeing is we're pulling the most promising match candidate out of a heap, evaluating how good it is, and sometimes that rules out a whole chunk of the search tree. So we let this run, and then finally we land on the best possible alignment. And the nice thing about doing this is that unlike some other multi-resolution approaches, you know that you've actually found the global minimum when you've done this properly with the decimate max operator. So what does this actually mean? We can go back to our figure from before. If we compare the ICP result with what we have here, you find that basically you don't get stuck in local minima. It just doesn't happen. So this is huge in terms of reliability. And the good news is that we can do this really fast. We can do searches in about 2 milliseconds, which allows us to try about 500 of these match candidates per second. So we had one laptop whose sole job it was to try to line up these little tiles. OK. There's a little snag. The snag is that if you use one of these approaches, whether you're using ICP or something else, you're going to get an alignment, even if the two places don't actually belong to the same place. right? It's going to wiggle around until you get the best possible alignment. And most of those alignments are not actually going to correspond to the truth. Now, the problem is, suppose that you take a bad edge, a bad match, and you put it into your SLAM system. So I might say that I'm in the same place as Dave, and so when I do the optimization engine is going to pull us together, and basically it's going to look kind of like you got a wormhole in space. Right? Very bad thing. We don't want that to happen. So we need a way of vetting these matches that we're generating at 500 hertz. Well, the basic idea is pretty simple. Suppose I have a whole bunch of these candidate edges. And let's suppose I find a subset of them that form a loop. Right? So I follow around 3 or 4 of these edges, and lo and behold, those edges form a cycle. Well, what that means is that I've got some constraint that really should get me back to where I started. Right? If I compose the rigid body transformations of any of these matches around a loop, I should end up with the identity matrix. If I don't, one of those edges is probably wrong. So what we do is we've got actually probability distributions for each of these matches. So when I compute the loop, I've actually got a distribution over what the composed rigid body transformation is, which allows me to compute a Mulholland-Nobis distance of how close we are to the identity matrix. And if that's really good, we allow those edges to graduate from the sort of holding area into our true graph. If you don't do this, you just get gibberish. All right. There's one other little wrinkle I want to talk about. That's basically terrain map compression. So bandwidth is really precious in this system. We had a total of 10 kilobytes per second of bandwidth to work with. That's shared amongst all 14 robots. Right? And that 10 kilobytes per second is assuming that you believe the manufacturer's data sheet, which I think we all know you shouldn't trust. So in reality, we had a communication budget of around 400 bytes per robot per second. It's not a lot. And we're trying to send over these 400 pixel by 400 pixel terrain maps from all the robots at about 0.7 hertz. We need to compress them somehow in order to make this work. So what we ended up doing was coming up a very simple predictive model based on a trivial graphical model. Basically, we learned the distribution for one pixel given its neighboring pixels. This is trivial to train with a bunch of training data. It's nice because it's compact. You only have 16 parameters. And yeah, it works great. So how well does it work? I'll skip over this briefly, but for those of you who are into compression, arithmetic encoding is Bayesian's best friend. So it basically allows you to achieve sub-bit per symbol encoding when you're doing compression. I'm going to skip over that for time. But the short version is that if we used gzip, you end up at about 380 bytes on average over our training data set. If you use the graphical model-based approach with arithmetic encoding, we're down to about 130 bytes. Right? This actually changed qualitatively the performance of our system overnight. Right? We went from being communication limited and having to slow down our robots because they were sending back too much data to being able to operate our robots about 3 times faster. So that was huge. And that's kind of an amazing fact, right? We're achieving 0.0475 bits per pixel. I think that's amazing. All right, so how did we do? So the contest was divided more or less arbitrarily into 3 different phases. The first phase looked a little bit something like this. This is about 250 meters by 250 meters. Excuse me. There were 6 of those red barrels hidden around the playing field. And we found and neutralized 5 of them, which was pretty good. And we didn't lose any robots, which I think actually might be the only team that didn't lose a robot in the first phase. Yeah?
Could you briefly describe scoring and whether time factored into it?
Yeah, so you were scored based on the quality of your map, the number of objects of interest that you found, minus some penalty for how much time you interacted with the system.
Okay, just the human time. So, for example, technically there could be no difference between a 14 robot team and a 3 robot team if they didn't use it. I mean,
right.
The robot team took.
Right, if you don't get an advantage from 14 robots over 3 robots, then you don't get any scoring consideration just because you brought a lot of robots. Right, so that's a great point because we went through the trouble of bringing 14 robots. We wanted to make sure that we actually got some benefit out of them.
I think the question is, do you have a set time to explore?
There was an upper limit of 3.5 hours, and everyone used the full 3.5 hours.
Okay.
Great, thanks for clarifying. Yeah.
It's probably worth mentioning there are constraints on the ratios of disruptors to not-disruptor robots and the maximum constraints there, because that changes. I think that means that you should have certain robots all the time if you can.
Yes, so there were a couple other constraints. The robots that were allowed to neutralize a target, you were limited to 3 of them. And so they form a sort of precious commodity. In addition, you had to maintain a 2-to-1 ratio between the sensor robots and the disruptor robots. So there was an incentive to bring more robots because then you're more likely to have a disruptor robot nearby. But there was definitely no scoring of how many robots do you have times 10 points. There wasn't anything like that. Good. So that's good. There's kind of a funny story here. I have a little icon here. It's a guy kickboxing. What the heck does that have to do with anything? So this was a kind of stressful competition. And Magician, the Australian team, was controlling their robots. And I guess one of their operators gets nosebleeds when he's stressed out. So during the middle of the competition, he just starts bleeding. And it's sheeting down. It's really coming down. I'm sorry, microphone guy. And so one of the judges comes over and he says, you know what you need to do? You need to take a napkin and stuff it in your upper lip. I guess all the capillaries that feed your nose go through your upper lip, so by stuffing something under there, you cut off the flow of blood. Sure enough, they stuff a napkin up there and his nose stops bleeding. Like, why do you know this? Turns out the judge is a competitive kickboxer. And it comes up on a regular basis. All right. The second round was a little bit different in that now we have some bad guys. In this case, the position of the bad guys is being screened to us as though there was an overhead predator keeping track of them. And what you see is we've got a bunch of robots cowering over here in the corner, trying to stay away from this guy until we actually are able to neutralize them. Then the robots sort of flood across, and they're going to get about here, and then they're all going to cower in the corner again until we can get the right geometry to neutralize the second bad guy, and then they'll stream out over the rest of the image. We actually just lost Robot 10. It was under autonomous control and wandered into the vicinity of the bad guy, and then was too slow to get away by the time you realized it was a bad situation. So you can see again our SLAM system sort of working online. It's not perfect, but again, this is a large area. It's 250 meters by another 250 meters. And so keeping it together in this well with 14 robots, I think is really an accomplishment that we're happy with. We found and neutralized both of the mobile OOIs. We missed one static OOI, which was actually this guy. Any guesses what went wrong? Yeah, it's on a red background. That was a problem. And also this guy is completely flush against the wall. So actually our segmentation had a hard time pulling this object out as not being part of the wall. Yeah?
What do you have to do to neutralize the mobile?
Yeah, the rule's a little different. You take 2 robots, and they both have to visually track the bad guy for some length of time. They're very sensitive about pointing lasers at people. But you could imagine that basically you're illuminating a target. All right, so that brings us to the third phase. The third phase was kind of interesting. Now, the third phase, there are more bad guys walking around. And they're also good guys. So just like in the real world, you don't want to drop a missile on a bad guy if it's going to hurt civilians nearby. Right? In fact, the scoring was brutal. If you injured a civilian, you lost all points for that entire phase. So in phase 3, what you had was a long corridor with a good guy and a bad guy basically holding hands, walking up and down. Right? Nothing you can do. So what you had to do is you had to sort of follow behind them, and then when they went around a corner, sprint into a corner and wait for them to separate, and then you'd have a chance to pick off the bad guy. And it was very, very difficult. There was very little margin of error. And we had a lot of trouble. So it reminded me of this clip from The Simpsons, where Bart and his friends are being bullied by the kids of Shelbyville. I'll just let this play out.
The lemon tree's gone. And the track's up here to lead into Shelbyville. We gotta get that tree back.
You'll be going to Shelbyville? We'll never make it out alive.
That lemon tree is a part of our town, and its kids, the backbone of our economy. We'll get it back or choke their rivers with our dead.
And that was our strategy, pretty much. So we sent wave after wave of robot. We had 14 of them, right? We'd send them in, they'd get blown up. We'd send in another one, it'd get blown up. And literally, we were choking off this corridor. The human has to step over our robots because we've just got dead robots everywhere. So this was actually, everybody had a very hard time on phase 3. This is what that death corridor looked like. Basically, you had to sprint from here to this corner because the bad guys were walking up and down here with a good guy holding hands. So we sent 5 robots in total to their deaths, then ultimately ran out of time, just like all the other teams. So the contest was designed so that we wouldn't, so that no team would be able to finish the whole competition. We're a little disappointed that we didn't get to see more phase 3, but that was hard. That was really hard. There was a funny conversation between the soldier and the judge. So imagine you're the soldier, and you're stepping over these robots. Now, our robots had text-to-speech engines on them. So every time they observed some sort of event, like detecting a person, they would utter an announcement. And it was the worst text-to-speech engine you've ever heard. We couldn't understand what it said. So basically, the guy's going through, and the robot's saying, "Oh-oi, oh-oi," which means object of interest. The guy had no idea what was going on. So he gets his radio and he says, "Base, I think the robots are talking to me." No, they weren't. They weren't. Okay, just a quick note here. There was a little friendly competition called the Old Ram Shed. On this, actually, UPenn won this little miniature competition. They did a fabulous job. We got bogged down a little bit. We had a robot. Our one mechanical failure was during this. We had a robot suffer casualty there. So we're going to try something real quick. What we have under here is a little maze. So I'm gonna hit the next button. The little block is gonna go away. I want you to just raise your hand when you've got a solution from the beginning of the maze to the end of the maze. Got it? Okay, go. Yeah, about 6 seconds in, almost everybody's got it. Right? This actually is one of my favorite examples because if you've got a map of the environment, which is what our robots are good at doing, it's really useful, right? If you're a soldier, you now have a good idea of where to go. You've got a mental understanding of the space that's really excellent. Now, one of the funny things about this phase of the competition was that if your robot breaks down, the rules required you to physically run in, pick up the robot, and carry the robot back out. Well, poor magician, they had a robot break right about here. And they found the robot just fine, but when they got in there, they couldn't find the way out of the maze. And so they're holding their robot, trying to figure out where to go. It really shows you that when you're in the maze, a map like this can be the difference between life and death if you're a foot soldier. This is actually our map from Old Ramshed, which is in here because this is our most kick-ass map of the Magic competition. It's a little smaller in scale. It's about 30 meters by 70 meters. So it's better in some respects just because there was less opportunity for something to go wrong. But still, this is a gorgeous map. One thing that the military likes about a map like this is that if you're looking in a village trying to find a weapons cache might be a volume of space where there's no door into it. Right? If you send in a brigade of troops, it's very easy to not notice that there was some square footage that you couldn't find your way into. But with a good metrical map like this, these sort of voids that you never saw are really clear. And that's a good thing. They're really interested in that. Okay, so we're going to wrap up the basic things that I think are important from this talk. If we want to make these autonomous robots really transfer to real-world applications, whether we're talking urban reconnaissance for the military or search and rescue type missions, we need to relax our dependence on GPS and prior information. We need to integrate humans into the decision loop. Right? The humans, for the foreseeable future, are going to know more than our robots, and not allowing the humans to inject that intelligence into our system is just going to hamper us unnecessarily. And multiple robots, we can make it work. Right? We can get the speed up of having large numbers of robots, which is going to help the operational tempo, and with any luck, we're going to find that we can actually use these teams of robots in these important environments. From our team, I would cite this consistent coordinate frame, right? Working really hard at the SLAM, making sure that you can keep everything coherent. That's what enabled the planning to work. It's what enabled everything to make sense to our one operator so that we weren't losing robots all the time. So I want to thank my team, and here's our website here. Some of our code is already posted. More will be posted with time. And maybe if there are any questions I can answer. Yes?
I have a few questions. So each of your robots has like a nodding control and some other sensors. So what was your total budget for this project? And the second question is, with the nodding LiDAR like that, you get 3D, but all your maps are 2D. So did you just like take a cross section when it was looking horizontally? And then third question is, you build some sort of sub maps rather than just taking a single line slice. Did you like drive for a while and make sub maps? And how did you go about deciding how to do that?
Okay, you might have to give me the Cliff Notes version. First one was on cost.
Yeah.
Our robots, fully equipped, cost $12,000, which is pretty amazing if you consider 6,500 of that is the Hokuya. Right, another 1,500 is the laptop. So our total budget was in the neighborhood of $250,000. 16 were fully equipped, and the other 8 we shared Hokuyas between the ones we sent to Australia. So when we went to Australia, we went with a Pelican case full of Hokuyas. Second question was about the 3D maps. So we're collecting 3D maps, but the tray maps I'm showing you here are 2D occupancy grids. So what we did is we didn't just pick a level and take a cross-section. We looked at the point cloud and we looked for the surface normal. And we basically recorded areas that were basically vertical. The heuristic being here that vertical surfaces were going to be the most useful, repeatable surfaces for the purposes of SLAM. And the third question, I'm sorry.
Did you build up sub-maps from
Right.
short time?
So every tile that we sent corresponded to exactly one traversal of the Hokuya. And we were moving during this process, but it was as small a tile as we could make it. The last thing we wanted to do, since these were sort of atomic building blocks for our SLAM system, we wanted to avoid any possibility that there would be an error within a single tile. So it was just one sweep, done, send it off. Great, good stuff. Yeah?
How often did your one operator intercede during the competition?
And so we had, which operator do you mean both
The
together?
main one.
What's that?
The main one.
The main one. They actually had about the same duty cycle. I'm going to have to do the math here. They didn't actually give us the numbers that they had collected, so we're estimating a little bit. We figured that our human workload was about 7% of a human per robot. So pretty good. So what does that map to over 3.5? I don't know. I can't do that. Any other questions?
Was there a penalty for eliminating wrong targets?
Say it again?
Was there a penalty for eliminating wrong targets?
People, yes. But if you just pointed a laser at a trash can by mistake, I don't think you got a penalty aside from it looking really silly. So there were actually 2 piles of points. There were the sort of objective points, and then there were the subjective points where it was like, how well did your system work? You know, qualitatively, how busy were your operators? You would probably get dinged for doing something that silly. And actually, one thing I forgot to mention that's kind of useful, I think we're the only team that provided an interface whose sole purpose it was to manage the cognitive load on the operators. So imagine that you have 14 robots. It actually takes cognitive effort to realize that nothing interesting is going on, right? And of effort that we can't really afford. So we had another user interface whose sole job it was to be blank until something interesting happened, and then a window would pop up and it would say, I've detected an IED. You know, I'm dispatching a disruptor robot to there. And then after the event went away, the window would go away. So this actually turned out to be a really useful thing in terms of managing the workload. And we got a report from the judges that the judges actually started watching our display to figure out what was going on. That's kind of cool.
How much better were you than the second team, and then the second team from the third team, et cetera? And what were some of the more common kinds of failures?
Yeah, so the first thing is that we weren't allowed to see the other teams run. So what we do know is limited to what we saw at the old Ramshed competition, which was the small version, and what we've talked amongst each other. I think the consensus amongst all the teams was that we won, but they never actually released the points. UPenn's system was very a little more minimalist. Their SLAM system didn't work very well, but they had a really effective way of watching what was going on in the robots, and the operators were really well practiced. So they just had a good way of kind of moving through the environment, detecting stuff. They didn't have as much autonomous stuff going on as we did. Razor also did very well. They had a nice SLAM system. It's hard to say whether ours was better than theirs or not. We had different sorts of failure modes. Yeah, Razor had a lot of trouble detecting autonomously the IEDs. And so they had a calamitous first 2 phases where they lost all of their robots within the first few minutes. Right? They just stumbled into a bomb, blew up, and they lost all their robots. So they basically just had to give up on phase 1 and 2. And that's what hurt them. Some of the other teams, Cappadocia, they had a beautifully engineered system, but autonomy was not their strong suit. If you looked at their OCUs, their operator consoles, they literally had like driving joystick, steering wheels and gas pedals. And it looked like they were set up to do tele-op, which they were. Their visual display was streamed live video from all of their robots. They used their 40 megabits per second to stream high-def imagery from all of the robots, and then mostly drove them. Right? So they did have some facility for autonomous operation. I know that because they told us about it, but I never actually saw it in use, so I don't know how sophisticated it was.
How did you resolve like inter-robot path conflicts?
Good question. So I mentioned that we had the 10 kilobytes per second as our main radio. We did have Wi-Fi radios as well. Now they were useless for command and control just because the range and the number of robots versus the size, you just couldn't get coverage. But what we did use the Wi-Fi radios for was to broadcast at a relatively high rate the position information for each robot. And they were actually sending out their position in their own private inertial coordinate frame, the corrections between which were sent out over the command control link by the ground control station. So the robots had, at a high rate of speed, position information and path information for all the nearby robots.
Okay.
Didn't say that very well. Does that make sense?
How do you avoid construct inconsistent maps if the robots are watching each other? I mean, at the beginning you show a video where all robots start from the same position, as all robots were, or many of them were able to see the other robots.
Yes.
So how do you avoid detecting those points that you see from the robots as part of the environment?
Right, so that's a great question. So why don't, and moving objects in general, actually, these things clutter up the map and make data association harder. So the first thing we did is the robots themselves didn't do the map matching. They took their maps, and if they included false positives because there were other robots or people walking around, they contained false positives. On the ground control station, we would take composites from multiple views of the same area and basically do sort of a occupancy grid confidence estimation thing. So if we saw multiple maps where an area was empty, and one map that said that there was somebody there, the empty ones would outvote.
So you had this nice way of finding false matches by doing sort of loop closure, and you said, well, if it doesn't match, then there's an error in one of those links. But you don't know which link it is.
That's right.
So what is your method for figuring out which it is, to figure out how to remove it?
So there's actually a logical error in what we did. So, but it mostly works. So what we know is that if a loop fails to validate because it's not the identity matrix, then we know one of them is wrong. And the rule that we actually implemented is if the loop is the identity matrix, then all 4 are right. Right? It's one of those A implies B does not imply that B implies A. Right? So, but it's almost true. Right? But the likelihood that you would get 2 edges where the error would just happen to cancel out, it didn't really happen.
So you can find other loops where that was correct, and then the one that was incorrect is the one that you couldn't validate by a correct match.
Right, so we never actually figured out which ones were responsible for the errors. When we found 4 that were self-consistent, we said, hooray, let's just run with those. So we had a background process that was taking all of these matched candidates, trying to find loops between them, and if we found a good loop, they would just graduate to the real graph.
And the ones that didn't work out would never make it.
They would eventually expire out of this background process. I think we've run over. I probably could give you guys a chance to escape, but I am very happy to field some questions afterwards.
Thank you.
Thank you.
There's an NREC TG at 5. I'm told NREC is bringing robots as well as food.